All right. Hello, everyone. So today we are back here for the AP Physics 1 free response questions. In these free response questions, as you can see, there are 5 questions for an hour, 30 minutes. So I am actually going to be splitting this video up into 2 parts. One for questions 1, 4, and 5, the shorter questions, and then one for questions 2 and 3, which are both the longer questions. I think that is going to be the best way in order to make these videos of approximately equal length then as well too. The second video will obviously probably be a little bit longer, but you know, it'll be about as even as I can get with them. All right, so let's go ahead and take a look at question number 1 then. So question number 1, we have 2 blocks connected by a string that passes over a pulley. Block 1 is on a horizontal surface and there is a string that is unstretched. Friction forces are negligible. Block 2 is released from rest, moves downwards before momentarily coming to rest. And the first part is saying that we need to explain in terms of only the forces exerted on block 2, why the block initially speeds up and why it slows down to a momentary stop. Now, in terms of thinking about this question, this is kind of an interesting one because thinking about it, I could definitely describe it with forces of the entire system. You know, as block 2 moves down, the spring force or the restoring force on the spring in the spring would cause block 1 to be pulled to the left. Therefore, it would pull block 2 back up as well. And so in terms of this, when it says only the forces directly exerted on block 2, we actually cannot talk directly about the spring force. So what I actually will have to say is that as blocked initially the tension is a lower value than m2 times g, which is the gravitational force on block 2. And therefore, block 2 would start with a net force pointed down. Now, it would not suffice to say that the tension is 0. In fact, that tension cannot be 0 to start. If the tension is 0, mass 1 would not move, and mass 2 would move on its own then. These 2 blocks are connected, therefore they are going to end up moving together. So I just have to say that the tension starts with a lower value. However, as block 2 moves down, tension increases and eventually becomes greater than FG2. FG2. I want to keep my same notation, which slows it back down. So tension changes, and eventually it becomes greater than force of gravity. That puts an acceleration opposite the direction of velocity, which then slows it back down and eventually will bring it to a momentary stop. All right, so part 2, derive an expression for delta y before coming to rest. In terms of this, it would not suffice to use, well, actually we could use energy if we wanted to. The spring is initially unstretched. And so in this case, what's going to happen is it will stretch over to its amplitude. And it's going to have to stretch the same amount that m2 actually falls. And in addition to that, I could actually use forces if I wanted to. However, I do think that it is actually significantly easier to go ahead and use energy. Reason being that we don't know exactly how large the tension force is going to be. We're going to have to do a lot more sort of thinking with that overall as well. So I'm going to go ahead and actually use energy then. So what I can go ahead and say is that we start out with just potential energy, right? There's no friction. So the potential energy, I could say that delta UG for block 2 will equal delta US for the spring. Now, what's that going to look like? Well, I'm going to have M2G delta Y is going to equal, and obviously this should be negative as well, technically. I'm just going to say that their absolute values are actually equal. Obviously, if one type of energy goes down, the other has to go up. So one of the changes would be negative, one would be positive. Anyway, change in spring potential energy will be 1/2 K delta Y squared. And so therefore, what I can go ahead and say is delta Y, K naught. Delta Y, I can cancel out one delta Y, and I'm going to be left with a 2 M2G over K naught then. And that is going to be my answer for delta Y then. Indicate whether the total mechanical energy changes as block 2 moves downwards. It does not change because there is no friction. So in the block's spring Earth system, there is no external force that remains uncancelled by another external force. So in particular, if I take a look at this, right, the weight force, so for example, I know that the gravitational force on block 1 is equal to the normal force of block 1 by the table. Those two cancel out, therefore they are not going to contribute to work done. In addition to that, also tension would cancel, and I'm going to put that in quotation. I'm going to put that in quotations, and the reason why is because the pulley only changes the direction of the force. Therefore, no work done on the system. I'm actually writing quite a bit here. If you wanted to, you could probably leave out the for example and giving all of those different different examples. Another way of describing this would say that the things that cause the system to speed up and slow down are just FG2 and the restoring force from the spring, and they are included inside of the system as well. That might be a more compact way of answering this question as well, if you so desired. All right, moving on to the next page. What we have here is a bunch of reading, and we do also have a lot of other stuff here too. So consider the system that includes the spring, Earth, both blocks and the string, but not the surface. And then what we have to do is let the initial state be when they're at rest before they start moving, and final when they momentarily come to rest. Energy bar charts, and we have to complete diagram B at which friction is non-negligible. Shade in the energies. Shaded should start at the solid line and represent any energy equal to 0 with a distinct line. Okay, well, that's easy enough then. We don't actually have to even explain anything here, but it's very easy to actually think about here, right? Friction is going to cause a loss in mechanical energy because the surface is not a part of our system. So we are going to actually have a lower spring potential energy. Gravitational potential energy would actually gravitational potential energy would still be present. So let me go ahead and erase this. And the reason why is because the blocks would no longer actually move as far. Friction would dissipate more energy. So I would actually expect to see some gravitational potential energy remaining, and then therefore the spring potential energy would not be as high as it should have been. In addition to that, friction is going to steal some mechanical energy. So instead of actually having So instead of actually having the two bars add up to 4 dotted lines, as you do in diagram A, they're going to add up to less than 4. And in this case, I would say that they're going to add up to 3, indicating that there is a loss due to friction. All right, and that is it for question number 1. Notice that we don't have to explain anything in part C. So that's pretty good then. All right, let's go ahead and move on to question number 4. I am actually pretty excited to do question 2. This is the first time we've had a gravitation question since the 2018 exam. But again, we'll save that for the next video then. All right, student has a piece of clay and a rubber sphere, both objects thrown horizontally at an identical block at rest, and friction is negligible. Both blocks fall to the floor. And so the clay will stick, rubber ball will bounce off. In the figure at the left above, the arrow represents the momentum immediately after the collision. And so then what we need to do in the figure to the right is represent the collision of the sphere block system in case B, the momentum of the sphere block system, that is. Okay. If the momentum is 0, if the momentum is not 0. Yeah, this is not too bad. All right. So the reason why this is not too bad is because both the clay and the sphere are of the same mass. In addition to that, what's going to happen, so what essentially happens is both systems start with the same amount of total momentum. And because the only forces in this system that are going to change the velocities while the collision is occurring is the force between the block and the clay or the block and the sphere, we would expect the sphere block system to have the same amount of momentum after the collision then. Obviously, the sphere is going to have less momentum than the clay. It'll be actually directed to the left. Therefore, the block would move faster, but I'm assuming that that's what the rest of the question is going to be dealing with. So let's go ahead and find out then. All right. Oh yeah, only one more part. This is the paragraph length response question. All right, so let me go ahead and actually switch over to text then, because that's going to make this a lot easier. Okay. After the clay and block A collide, block A lands a horizontal distance. Does block B land at a horizontal distance greater than, less than, or equal to dA? Well, the answer is going to be greater than. So block B lands at a horizontal distance greater than that of block A. Now, obviously, this is a paragraph length, so I do actually have to go ahead and write a full paragraph. So this is because, and I'm just going to go ahead and outline my thoughts as I'm writing this, because I kind of already have an idea in mind here. This is because the sphere experiences a greater magnitude of impulse than the clay, and so therefore exerts a greater impulse on block B than block A, than the clay does on block A. And in quotations, not quotations, parentheses, that's the word, in parentheses, due to Newton's third law, which states equal opposite forces. So due to Newton's third law, this means that block B has a larger speed than block A. When the two blocks leave the table, their horizontal velocities remain unchanged. They start at the same height. They reach the ground at the same time. Actually, I think I can just go ahead and jump to that. They reach the ground at the same time due to starting with the same height. In this sentence, I'm actually going to change it, and this means that block B has a larger horizontal velocity than block A. I think that's quite a bit clearer then. Okay, they reach the ground at the same time due to having the same height, and therefore block B travels farther horizontally. All right, and there is my paragraph, excuse me. Let's go ahead and actually change the color. There we go. You should be able to read that a little bit better now then. So you can go ahead and take a read at that. Feel free to go ahead and pause the video if you want to read that in its entirety. Make sure that it makes sense to you as well. This is actually a very interesting little paragraph. Nice and actually pretty quick to reason through then. All right. So then the final question that we have for today is question number 5. A spring of unknown spring constant is attached to the ceiling. A lightweight hanger is attached to the lower end of the spring, and a motion detector is placed on the floor facing upwards directly under the hanger. Bottom of the hanger is 1 meter above the motion detector. We place a 0.5 kilogram object on the hanger, allow it to come to rest, and the spring is stretched downwards some distance from equilibrium. And so we're getting height as a function of time. Okay. Okay, now I actually have to go ahead and get rid of the text, unfortunately. There we go. All right, height as a function of time then. Okay, using the information from the graph, calculate the spring constant. How do we do that? This is an oscillatory question. And so therefore, what I can say is that the period is equal to 2 pi root mass over spring constant. Therefore, spring constant is going to be t squared over 4 pi squared. Sorry, this should be m over k. Therefore, k will be 4 pi squared mass over period squared. Now, in terms of what the period actually is, the period is 1.25 seconds. How do I find that? It's just peak to peak or valley to valley in the question. I did valley to valley because it's far easier. So let me go ahead and actually compute this out. Now, the number that I am going to get in this case, let's see. So mass, I believe, was 0.5. Yeah, 0.5 kilograms. 4 pi squared mass over period squared then, 1.25 seconds for the period, remember. That gives me a value of 12.6 newtons over meters. And that is the value of my spring constant then. All right. Now for time 0.75 seconds, the object spring Earth system has some kinetic energy, K naught, and total potential energy, U naught. 1.13 seconds, it again has that as well. Interesting. Okay. Explain how a feature of this graph indicates that the total kinetic energy is the same at both times. Well, this is actually not too bad as well, because this is a height as a function of time. So therefore, I calculate the slopes of the tangent lines at both times to find the velocity. To find both velocities, rather, because both tangent lines have the same slope. The object would have the same speed. In both cases, at both times. Therefore, same kinetic energy. All right, briefly explain why the total potential energy is the same at both times. Now, if I go ahead and I take a look, 0 points, just so I can kind of eyeball this a little bit better, here's where height as a function of position is right here. And then in terms of 1.13, that's going to be approximately right here. So the reason why we are going to have the same potential energy in both cases then is because at time 0.75 seconds, the mass is located farther, at a higher height, rather. Let me just say that, at a higher height. Now, okay, that's fine. I mean, that doesn't really tell us much on its own. So something else I do have to say is that the mass, or the spring, rather, is stretched more at time 1.13 seconds. Therefore, I have more gravitational potential energy at 0.75 seconds and more spring potential energy at 1.13 seconds. So there we go. Now, in terms of this overall, let me actually go back to the previous slide. I'm a little bit curious on something. So what it does tell us is that if you just have the lightweight hanger, then the bottom of the hanger is actually 1 meter above the motion detector. So what I can actually go ahead and do is I can actually go ahead and elaborate a little bit more on my answer to part B, part 2 then. So I'm actually going to go ahead and do that then. So at 0.75 seconds, gravitational potential energy is mgh, which is going to be 0.5 times 10 for g, and then the height looks like to be approximately 0.64. Meanwhile, the spring potential energy, which is 1/2 kx squared, is going to be 1/2 times 12.6 times, and that's actually going to be 1 minus 0.64, right? That's the displacement from the equilibrium. So that's going to give us 0.36 squared. So let me actually go ahead and compute both of those out. So spring potential energy, 0.81648 joules. Obviously, I wouldn't have that many digits for my final answer, but I'm just putting them there just so we can kind of see how they're all going to add together. And then likewise, gravitational potential energy, 3.2 joules. Now, if I go to 1.13 seconds, then what I'm going to see is that I'm at approximately 0.56 meters in terms of height. So therefore, gravitational potential energy is going to be equal to, and you can double check this using the formula if you want, but it's going to be 2.8 joules. Spring potential energy is going to be equal to, well, if I'm at 0.56 meters, then that's going to be a 0.44 displacement from equilibrium. So times 0.44 times 0.44. Then I'm going to get spring potential energy equal to 1.21968. So if I go ahead and I add both of those values together, I get approximately 4.02 joules at 1.13 seconds. And then if I go ahead and add the values at 0.75 seconds, I'm at approximately 4.02 joules again. So adding both of these together would get me total 4.02 joules. So I'm going to see that however much the gravitational potential energy falls, the spring potential energy rises. And so what I should say is that these, however much UG is between the two times, delta US is the same. All right, there we go. The experiment is repeated with a spring of spring constant for K naught that has the same length as the original spring, and you hang a 0.5 kg object from the new spring. Determine the new equilibrium position. Well, at equilibrium, I know that the restoring force should be equal to the gravitational force. Therefore, K delta Y is going to be equal to mg. Therefore, what I'm going to end up having is delta Y equals mg over K. So therefore, what I would actually expect is I would expect the new equilibrium position above the motion detector to actually be 4 times less. So therefore, delta y is 4 times less. Now, something to note is that the graph showed delta y equals 40 centimeters. Therefore, the new position is going to be at 90 centimeters. Sorry, not the new position, the new height is going to be at 90 centimeters. I decreased the displacement by a factor of 4. 40 divided by 4 is 10. 1 meter minus 10 centimeters is 90 centimeters. All right, so for part C, part 2 then, well, part C, part 1, we determined that the new equilibrium position was 90 centimeters. So it says that the object is pulled down the same distance from the equilibrium position and released. Draw a new curve. Well, period is proportional to 1 over root k. Therefore, the new period is actually going to be half of the old one. So it's 0.625 seconds. So if I start something like right here, then what I would expect to see would be something like it repeats. It's up right here, goes up to the top around right here, repeats at 1.25 and approximately 1.875. So I would expect to see something like this. Now, equilibrium would be at 90. I'm pulling the spring down 5 centimeters. So I'm actually going to go ahead and make this 85, this 80, this will be 95, and this will be 100 right here, just for the sake of simplicity right here. And so therefore, I would expect the graph to look something like this then. All right, this is a little bit kind of tricky for me to draw. I apologize about this, but hopefully this kind of makes sense right here. You see that there's more oscillations because it's got a shorter period then. Period goes down because spring constant goes up. And then in addition to that, what you're going to see is still the similar type of function, but just with different values now as well. All right. Yeah, there we go. And I think that's how the graph should look then. All right, let's go ahead and see. I think that should be the last. Yep, that's the last part. Yeah, so that does it for this video then. We've successfully completed questions 1, 4, and 5 for the AP Physics 1 free response questions for the 2022 exam. Thanks for watching. Again, in the next video, we'll go ahead and cover questions 2 and 3. The experimental design and the qualitative quantitative question with the gravitation, as well as presumably a rotation question as well too. I haven't actually looked at these 2 yet, so I'm looking forward to doing that with you guys in the next video then. As usual, I hope that you learned something from this. Thanks again for watching, everyone, and I'll see you all in the next video. So take care, everyone.